We've seen a couple of gas laws. We've seen Boyle's law and Charles's law. We're going to fill this column today with the remainder. Boyle's law and Charles' law both do the same thing. You set yourself up a set of working conditions, and then you make a change. So there's a pressure-volume relationship at the beginning. That's a constant. And it remains constant all the way through your day. And so if you know one of the variables at the end, you automatically know the other one. So questions for Boyle's law and Charles's law say, I set this thing up. I have a volume and a pressure. And then I change the pressure. What happened to the volume? I changed the volume. What happened to the pressure? I changed the temperature. What happened to the volume? So these are all about change. And if there is a pressure-volume relationship and there is a volume-temperature relationship, then there has to be a pressure-temperature relationship as well. This one is kind of unnecessary because you can get to this information with just these two, with Boyle's law and Charles's law. But what Gay-Lussac's law says is that pressure and temperature follow this relationship, which makes sense that at a given temperature, the gas particles are moving with a certain kinetic energy, with a certain speed. And when you elevate the temperature, you elevate the kinetic energy, you elevate the average speed, but also the number of high energy collisions. And it's the collisions that cause pressure. So when pressure goes up, temperature goes up. We saw that with the same thing, with when temperature went up, volume went up. So these kind of fit. Let's do one. A gas has a pressure. Let's say it's a little bit elevated. It's higher than atmospheric pressure. It's 1.5. What would you like the new temperature to be? Give me a temperature.
50 degrees.
Okay. So what is the new pressure at 50 degrees Celsius? Let's read from the question. I have 4 variables, P1, T1, P2, and T2. And these two are a matching pair, that when the temperature is 25 degrees Celsius, the pressure is 1.5 atmospheres. Pressure 2, the new pressure, that's the thing we're being asked to find. temperature 2 gets to be 50 degrees Celsius. T1 over T1 equals P2 over T2. And the thing that we're trying to find is P2. That means I have to move this T2 out of its way. So that T2 goes across the equal sign. Currently it's a denominator. It crosses the equal sign, it's going to switch and become a numerator. So P1 T2 over T1 gets to be P2. All right. And then maybe we can just put the numbers in. Nope, cannot just put the numbers in. This has to be in Kelvin. This is going to have to be in Kelvin, because what if, instead of saying that the temperature started at 25 and went up to 50, and we'll leave it there because that's a student-generated number. But what if I had said the temperature went down to 0? 0 degrees Celsius is just ice temperature. So now you have a 0. 0 is temperature 2, and that means you take P1, whatever number that is, and you multiply it by 0. That makes my answer invalid, because any number times 0 is 0. So we can't keep this in Celsius. This has to be converted into Kelvin. Okay, so go ahead. What's our conversion factor for Kelvin? Plus 273. Makes this 298K. And 323. Okay, now you can put the numbers in. And this will work no matter which one of the myriad of units for pressure you choose to use, whether this question was in millimeters of mercury, or bars, or pascals, or kilopascals, or atmospheres, the one that we're choosing to use. Doesn't it matter? It just reads, because that's in Kelvin and that's in Kelvin. Those Kelvins cancel. So I put in 1.5 atmospheres times T2 goes on the top, 323 divided by 298. And that gives me an answer that's in atmospheres, because that Kelvin and that Kelvin just cancel each other out. Okay. So we're going to do a couple of things with these questions. Write yourself a table. Always write yourself a table, even when it's not a particularly difficult question. Assign the values out of the question to the table. Go to the gas law itself, write it down, and then just use algebra. It says if P1 over T1 equals P2 over T2, then P2 is P1 T2 over T1. Then you put the numbers in, and you get an answer. And that answer needs a number and a unit. What is the number?
1.6.
Okay. And then you ask yourself, does my number make sense? So Gay-Lussac's law says this: when temperature goes up, pressure goes up. Did the temperature go up? Yeah. Did the pressure go up? Yeah. So your answer's probably right. Moving on to the next one. Okay? At the end of everything that you do, make sure that your answer has a magnitude, and sometimes they have a direction. Energies definitely have a direction. And that has a unit, and then just take a second and say, is this a calculator error? Does my number make sense? Does it follow what I'm expecting it to do? Yeah. Temperature went up from 298 to 322. Pressure went up from 1.5 to 1.6. If we'd have left this in Celsius, we'd have doubled the temperature in Celsius, which would mean we're expecting a doubling in pressure. And that's not what we got because we're not allowed to use Celsius. There's another rule. This is Avogadro's law. And Avogadro has already told us that there is a molar volume for gases. Avogadro says that 1 mole of gas, any gas, and look, the questions from Wednesday and the questions from today, this gas is unidentified. It never said this was argon, or nitrogen, or carbon dioxide, or methane. It just says it's a gas, because the math works for all of them, independent of what they are. 1 mole of a gas occupies 22.4 liters. That's the important thing that we're going to come back to. Avogadro says, if I have a mole of gas, any gas, and I put it in a balloon, that balloon will inflate to 22.4 liters. If you have 2 liters of gas, then your balloon will be twice as big. Avogadro says when the number of moles goes up, the volume goes up. When the number of moles goes down, the volume goes down. Okay, which makes sense in our real world, because if I blow a balloon up and that balloon has a pinhole in it, then gas escapes out of the balloon into the environment. As the number of moles of gas inside the balloon decreases, the volume of the gas decreases. Okay? So this one's slightly less useful, this law. But it says that the volume of a gas, when you divide it by the number of moles, is a constant. And when N is 1 mole, the volume is equal to 22.4 liters. And if I change the number of moles, then I change the volume. So unless we're asking you about, hey, you have a balloon and it's got a hole in it, and at the end of the day, you've got less gas in the balloon than at the beginning of the day, unless we're asking you something like that, then we're not going to be using this. The time that we use this is that we pull it all back to that magic number, the 22.4. That 1 mole is 22.4. Therefore, I can access volume just by knowing number of moles. Here's a question. One mole of helium occupies 22.4 liters. All of the questions that have been on the board from Wednesday through today all need to come with a second sentence that says, bear in mind the other variables don't change. So if I just asked, what did I just ask? Pressure versus temperature. I had a temperature, I changed the temperature. What was my new pressure? Bear in mind, the size of the container did not change. So volume didn't change, plus no gas was lost to the environment. So the number of moles and the volume didn't change. And here it would be the number of moles and the pressure didn't change. And there it would be the number of moles and the temperature didn't change. Okay, we're changing two of the variables at a time. We're leaving the other two alone. 1 mole of helium occupies 22.4 liters. What volume does 1 gram of helium occupy? Oh, I've got to add a little bit of blurb here. At STP. STP is standard temperature and pressure. And for gases, that is 0 degrees Celsius and 1 atmosphere. So 273 Kelvin. And 1 atmosphere. We've seen standard conditions before. Previously, we saw them for solutions. We did standard enthalpies, where we took solutions and mixed them together and measured out how much heat was taken in or given out during a reaction. They were all performed at room temperature and pressure, which is 25 degrees Celsius, even though they're called standards. Standard conditions for solutions can't be at 0, because if you put a solution that contains water at 0, you get ice, and I don't have a solution of stuff moving around anymore. Okay, so I have a V1, I have an N1, I have a V2, and I have an N2. And V1 can be 22.4 liters, and N1 can be 1 mole, and V2, well, that's the number that I need to find. It's asking me, what is the volume of a gram of helium? And N2 is, oh, the question doesn't have that. So I have to figure that one out. It doesn't give me moles, it gives me grams. How do I turn grams into moles? Moles equals mass divided by formula mass. So what goes here is another question mark. N2 is the moles of helium, which is equal to the mass of helium divided by the formula mass of helium. I have 1 gram of helium, and I'm going to divide it by what the periodic table tells me the formula mass, or in this case, the atomic mass of helium is. What is that number? 4.002. So let's just have it be 4. This will be in grams per mole. So the grams and the grams cancel. and the per mole rises up to the top to give me an answer that is in moles. All right, break out the calculator. 1 divided by 4. And 2 is 0.25. Okay. So V1 over N1 equals V2 over N2. I know V1, I know N1, I know N2, I need to find V2. So I have to move the N2 across the equal sign. And when I do, it stops being a denominator, starts being a numerator. There you go. Put the numbers in, come up with an answer.
6.
5.6 what? Liters. So V2 gets to be the initial volume, 22.4, times the new number of moles, 0.25, divided by the original number of moles, which is 22.4. Cut in half is 11.2. Cut in half again, 5.6. Okay. These two are the big ones, Charles and Boyle's, right at the top. These are the ones show up a bit. All right, questions? Fairly straightforward. Let's look at what we've got. All these gas laws, all telling us how these 4 variables, pressure, volume, number of moles, and temperature, all interact with each other. Okay. Let's look at this. Because what it says on the left is equal to what it says on the right. Because pressure times volume is equal to a constant. Volume divided by temperature is equal to a constant. Pressure divided by temperature is equal to a constant. Volume divided by number of moles is equal to a constant. With everything equaling a constant, I think there might be some interconnectedness here. The pressure in P1V1 equals P2V2 is a numerator, as is volume. In Charles's law, volume is a numerator. In Avogadro's law, volume is a numerator. In Charles's law, temperature is a denominator. In the Gay-Lussac law, temperature is a denominator. Pressure is always on top of the equation. Temperature is always at the bottom. Volume is always at the top. Number of moles is always at the bottom. Where this is heading is I can put this all together. If pressure is always a numerator and volume is always a numerator, And the number of moles is always a denominator, and temperature is always a denominator. All four of those can combine to give me a constant. This constant goes by R. R is the universal gas constant. PV over NT is equal to a constant is going to be called the ideal gas law. Gases behave ideally when you catch them in an environment where you make it likely that they're gases. High temperatures, big volumes, low pressures. Keep them away from wanting to turn into liquids. If you make the temperature really low, gas is going to want to turn into a liquid. You make the pressure really high, gas is going to want to turn into a liquid. Here's where things get a little bit complicated. This is Wikipedia. If you go and you look up the universal gas constant, it will tell you this is the value of the universal gas constant. And it's the only time that you will see that a constant can have different values. You were told all the way from middle school upwards that a constant is a constant is a constant, that it's a number and that number is a number. Well, that's great, but this is science. And the number is what it is based on what you feed it. If you feed it a volume that's in liters and a pressure that's in atmospheres, that number will be different than if that was in fluid ounces and this was in pounds per square inch, because nobody would ever use those units because those are crazy units. But you could, because pressure is allowed to be bars, torr, atmospheres, pascals, millimeters of mercury. It's allowed to be all of these different units. If you change this unit, then you change the value of P, which means you change the value of this constant. The big two, there's really three on this list, are here. That one right there. Liters, atmospheres, Kelvin, and mole. Liters, atmospheres per Kelvin per mole gives me a value of 0.0821. That's the number we're going to use. If you stick around and you take chemistry 2, you get to use the value of R twice in chemistry 2. One of the times it's 0.0821 liter atmospheres per mole per Kelvin. And the second time around, it is 8.3144 joules per Kelvin per mole. Because those two things are asking very different questions. One of them has joules in it, because he's asking about energy. And they've converted pressure, which is a force, into an energy. The other one is this one, and it's the same number. It's 8.3144, but that's in pascals and cubic meters. Pascals are the SI unit of pressure. They're not the best unit of pressure. There's 101,000 pascals in an atmosphere. And cubic meters. It turns out that the liter is not the SI unit for volume, that the cubic meter is. But nobody uses that. We all use liters. So this one that we're going to use today, liter atmospheres per Kelvin per mole, that's the most convenient one. But you have to be aware that the number of R is going to change based on its application. So this is 0.0821 liter atmospheres per mole per Kelvin, or 8.3144 joules per Kelvin per mole. We will see this later. Okay, that's not the one that we're going to use today. What you have to do is make the units in the constant match the units that are in your question. Okay. So we have one last law. It's called the ideal gas law. And PV over NT equals R is where we are right now. I'm going to take that N and that T and move them across so that I don't have any divisions, that everything is all on one line. And it rearranges to be PV equals nRT. Questions about PV equals nRT are different than Boyle's law and Charles' law questions because they don't ask about a change. What happens with an ideal gas equation question is we throw numbers at you and you find the missing value. It's not going to be about, hey, I changed the temperature. What happens next? There's none of that. There's no wording that involves change or new. Let's do one. You're looking at me. Give me a number.
Like a decimal or just?
Yeah, sure.
20.2.
Who else is looking? Mariah, you looked. Give me a guess.
Hydrogen.
Okay. Hydrogen? Is that what you said? Okay. Hydrogen has an atomic mass of 2 grams per mole. That means that 20 grams of hydrogen is 10 moles. How many liters is that going to want to be? 224 liters. So we're going to need a big vessel. Give me another one.
Oxygen.
Okay, now oxygen weighs 32, so that's a bet. So this is what I do when I write questions down. I mean, you make this stuff up on the spot, but then you know, oh, this is going to be an enormous number. Right? If it were hydrogen, it was going to be an enormous number. So 20.2 grams of oxygen gas is contained in a 5 milliliter flask. Information, information, information. We're feeding you values. What? Oh, I'm not done. I'm missing something. Temperature. I need a temperature.
20.
Okay. This is what a PV equals nRT question looks like. There's no, I set this up, I made a change, what happened to my sample? This says, take these values, find the missing number. Excuse me. So, we're going to make a table. You're going to make a table. You're going to put the numbers in the table. And when the numbers in the table match the value of the constant, then you're allowed to put them in the equation itself. R is 0.0821 liter atmospheres per mole per Kelvin. So if my temperature is not in Kelvin, I cannot proceed with the equation. If my amount is not a mole amount, because it's a gram amount, I cannot proceed with the equation. If my volume is not in liters, then I cannot proceed with the equation. I've got to make sure that my volume is in liters, my pressure is in atmospheres, my moles are in moles, and my temperature is in Kelvin. 20 grams of oxygen is contained in a 5-liter flask at 20 degrees Celsius. What is the pressure? What is the pressure? Pressure is the missing value. But I can tell you that it's going to be in atmospheres because it matches the constant. Volume, I slipped up. I could have given that to you in milliliters. It's Thanksgiving. Accept the gift. They haven't ruined Thanksgiving yet by making gift exchange a thing. Just keep it that way. Volume is 5 liters. Number of moles. Well, number of moles is currently missing. But moles is mass divided by formula mass. So the mass of oxygen divided by the formula mass of oxygen is going to be the number of moles. And the mass was 20.2. And then the formula mass, periodic table, thank you. Each oxygen is 15.994. So let's make that be 16. 2 16s, 32. Grams divided by grams per mole gives me a number that is moles. I don't know what that number is because we just made that one up. So someone has to tell me what that number is. What is 20 divided by 32? 20 divided by 32 is the same as 10 divided by 16, if that helps, which is the same as 5 divided by 8.
0.63.
Does anybody else agree? Yes. And we can move on. Temperature. Temperature is 20 degrees Celsius, but degrees Celsius doesn't match the value of R. So I have to adjust it. I'm going to add 273 to that. Shouldn't need a calculator for that one. 293. Okay, temperatures in Kelvin, moles are in moles, liters are in liters, atmospheres waiting to be found are in atmospheres. Now you've got the permission to put the values into the equation. PV equals nRT. I need to find P. If PV equals nRT, what does P equal?
RT divided by V.
The V moves across the equal sign, ceases to be a numerator, becomes a denominator instead. Put the numbers in, and out pops the answer. I remember being told to write the units in my calculations and just not wanting to do it because it felt like it was extra work. It feels like it's extra work, but it keeps you on track. It stops you from messing up. Okay. The liters and the liters cancel. The moles and the per mole cancelled. The Kelvin and the per Kelvin cancelled. The only unit that hasn't cancelled is atmospheres. Okay. Looking for somebody else to corroborate that number. It's a little bit higher than I'd planned, but I can believe that.
At 3.03.
Okay.
I also have 3.03.
Okay. Do it again. 3 atmospheres. Sounds about right. Okay. I have 20 grams of oxygen, and that gives me, because oxygen has a mass of 32 grams per mole, it gives me less than 1 mole. Okay, so half a mole would go into 11 liters at 0 degrees Celsius. No, yeah. So I am squeezing it down. So my pressure will be elevated. The pressure inside this flask will be above atmospheric pressure. That's about the right number. I think it's about 3 times normal. So you just had a calculator error of.
Miss the 0
Mm-hmm. Oh, there you go. It is a 0.0821. There you go. So what would happen where you come back and you'd go 30 atmospheres. Okay, let me think. If this is so we would not be able to do that experiment with 30 atmospheres in anything glass, because 30 atmospheres confined into here would be like explosively dangerous. So we would have to reinforce a metal tank. I could easily put three atmospheres in glass this thick. That would be no problem at all. Okay, all right, great. Have a good Thanksgiving break. We'll revisit all of this when we come back, because who's going to remember? I mean, seriously, who's going to remember any of this? And then we're going to modify it with mixtures, because the gases are gases are gases. The laws work whether the mixtures or the pure. Okay? Have a good Thanksgiving. Come back safe.